Good morning. My name is Jivinasai. I am here to present the PPT on unitary matrix constraints. The subject is linear algebra and calculus. My roll number is R2. I am from CSCD section. Let's go to introduction. A unitary matrix is a square matrix whose conjugate transport is its inverse. In other words, if U is a unitary matrix, then U into UT is equals to I, where I is the identity matrix. The constant of the unitary matrix can be understood in terms of its properties. Some of the important properties are unitary matrix are the columns and the rows of a unitary matrix form an orthonormal basis of vector space. In this unitary matrix, the columns and rows of unitary matrix form an orthonormal basis of a vector space. The determinant of unitary matrix has a magnitude of a and a complex A phase of 0. The eigenvalues of unitary matrix have a magnitude of 1 and a complex phase that can be any value. Let's go to the applications. As opening the paragraph of states, many signal processing tasks involve constrained minimization of function TR, where is a possibility time varying covariance matrix. Where is a possibility of time varying covariance matrix if the constant is, then it is given by now well known that the minimum occurs when the columns of span the same subspace as span the eigenvectors associated with the smallest eigenvalues of. This is an example where for a unitary matrix. Other problems in linear algebra can also be expressed as orthogonally constrained minimization of problems include finding the singular value, decomposition of matrix, and computing a total least square solutions. Whereas in iterative methods such as those presented here have yet to outperform traditional methods for solving linear algebra problems in general. One advantage of iterative method is their applicability to adaptive engineering applications where minor corrections to present estimates need to perform regularly. Another advantage is their computational robustness. Iterative refinement can be used to improve solution obtained by relation means. The weighted low rank approximation problem is to find a matrix having specified rank and that best approximates a given matrix under a weight norm. It is shown in that the weighted low rank approximation problem can be reformulated as an orthogonally constant minimization problem. One, because it uses the least possible number of parameters. A similar idea is used in to reformulate the reduced rank winner filtering problem as an orthogonally. In this summary, significant number of engineering problems can formulated naturally as an orthogonally constrained minimum problem. The present paper not only provides novel algorithms for solving such problems, but it provides a general framework in which existing methods can be better understood. The present paper breaks with a tradition by not moving along geodesics. So the reason for this is now explained. There is no inherent connection between the geometry imposed in the constant surface and arbitrary surface. Uh, that is to say, although moving all along the geodesics that can be done. A disadvantage of moving along geodesics is the computational cost involved in computing the path of a geodesics. So in this reason is no inherent connection can between the geometry imposed in the constant surface can be imposed at the geometry of cost function. That is to although moving along geodesics is sensible thing. So only sensible thing can be done in a disadvantage of moving along geodesics is the computing path of a geodesist. So here are the graph of the unitary constraint. Graph 1 comparing the converge rates of steepest descent and inverse reiteration algorithms when applied to the matrix A is equals to diagonal 1, 1.01, 1.02, 1.03, 1.04. So let's go to next graph, that is figure 2. Graph comparing the converge rates of the steepest descent and inverse reiteration algorithms when applied to the matrix A diagonal 1, 2, 3, 4, 5. Here is the graph. of the third. Graph comparing the converge rates of steepest descent generated between 20 by 20 matrices with eigenvalues uniformly distributed between 10 and 11. Here's the graph, and let's go to figure 4 graph. For the graph comparing the convergence of rates of the steepest descent and inverse iteration algorithm when applied to 10 randomly generated 20 by 20 matrices with eigenvalues uniformly distributed between 0 and 1. A connection function. Let's go to the next topic, that is, as mentioned earlier, the local parameterization used in this paper is computationally simpler to compute one that one. The asymptotic rate of convergence of modified Newton algorithms there is here is the same as the for Newton methods. That is, they all asymptotically achieve a quadratic rate of convergence. However, for given cost function, it can be expected that one algorithm will converge faster than the other one. As connection function was also given to the manifold. Doing this made it is possible to calculate the gradient and Hessian of function on this manifold. Roughly speaking, the classical formula for computing the Newton step was generalized by replacing the first and second order derivatives in the Newton's formula by gradient and Hessian of cost function on the manifold. Newton's formula results in a vector pointing in the direction to move. Since following a geodesic corresponds to walking in a straight line, it is natural for it to interpret Newton's formula as requiring the Newton step to step eluding geodesics. So the motivation for considering for different approach in this paper is that there does not seem to an interesting connection between the remain geometry of the step. Conclusion: this paper developed novel algorithms for the minimization of cost functions subject to the constant. The key feature of the algorithms is that they reduce the dimensionally observation problem by reformatting the optimization problem as an unconstrained one on other the Stiefel-Grassmann manifolds. So a consequence of this is that the converse properties of algorithm may be different from those to traditional methods. The verify acceleration algorithms were applied to the problem on finding eigenvector associated with the smallest eigenvalue of arithmetic matrix. These are the references, and so these are the references below. 3 references, 4 references. So thank you.